Welcome to another lesson from Transparent Physics, and in this episode we are going to be discussing elevator physics. And elevator physics is an excellent opportunity for us to try out a lot of the one-dimensional dynamics that we've been discussing so far this unit in sort of the controlled environment of the elevator. So let's get started. The goals of our lesson include discussing how the forces act on you in an elevator. And specifically, we're just going to focus on starting at the bottom of a building and going upward, although we will talk briefly about starting higher in a building and going down. In addition, we're going to try to connect the forces, sort of the quantitative forces, to the more qualitative sensations that you experience as you're riding in an elevator, and try to explain how sometimes what you're feeling doesn't always correspond with what's actually happening with you. In the analysis of an elevator, it's really a tale of two forces. And the scenario is as follows. You go into an elevator holding a bathroom scale, you set the bathroom scale down, and you stand on the bathroom scale. So in that scenario, there are two forces of interest that act on you as the elevator passenger. There is a constant force acting down on you from your weight. Your weight is not going to change ever in the elevator. Your weight is constant. On the other hand, there is a force pushing up on you from the bathroom scale. And as we go through the different scenarios, we'll see how those forces interact with each other to create all the motions that we need throughout an elevator ride. And just as a default, we'll bring Frank in. Frank has a mass of 91.8 kilograms. Starting at the bottom, Frank has walked into an elevator. He's set down his bathroom scale. He's standing on his bathroom scale waiting for the elevator to start. And Frank's mass of 91.8 kilograms means that he has a weight of around 900 newtons. Weight is mass times gravity. Frank's weight is based on his mass. His mass is never going to change. His weight is never going to change. And we have the 900 newtons in there for the magnitude, and the negative sign in for the direction, because force is a vector and should have a magnitude and a direction. So gravity, aka the force on Frank by gravity, aka his weight, is pulling down on Frank, represented by an orange arrow. Now, Frank is pushing down on the scale due to his weight. So there's a force on the scale by Frank, which is equal in magnitude to the force that Frank pushes down on the scale with due to his weight. So the force on the scale by Frank, the blue arrow acting down, is also negative 900 newtons. And according to Newton's third law, if Frank is pushing down on the scale pushes up on Frank. So that is the other force acting on Frank. It's an upward directed blue arrow, and that is also 900 newtons acting upwards. So to summarize, what we have is gravity is pulling down on Frank. Frank is pushing down on the scale with a force that's equal to the gravity. And Newton's third law says, if you push down on me, I push up on you. And we have a force up on Frank of 900 newtons. Zooming in specifically on Frank, we only look at the forces that act on Frank. So I'm not worried about the force on the scale by Frank right now. So we've eliminated from the picture. All I'm worried about is the forces acting on Frank. So there is a force acting up on Frank of 900 newtons. There's a force acting down on Frank of 900 newtons. So if we analyze the math, we can see that the forces are balanced. Newton's first law says when the forces are balanced, there's no change in the motion. Since he's at rest, he's going to stay at rest. So in a question that may seem trivial in this particular scenario, we're going to ask ourselves, what does Frank feel? Well, Frank has a force acting on him by gravity pulling down, and then there's a force acting up on him from the scale that's equal to his weight. And we get cues about our weight from how we interact with our environment. The surface pushing up on us is one of the ways that we interpret our weight. If the surface pushes up on us more, we feel like we weigh more. If the surface pushes up on us less than we're used to, we feel like we weigh less. So we take a cue from that upward blue force. And since in this case, the force acting up on Frank is equal to his weight, he just feels normal. He doesn't feel heavier. He doesn't feel lighter. He just feels kind of Frank. So let's pause briefly and talk about the role of the bathroom scale in all of this. The humble bathroom scale tells us the amount of force that is pushing down on it. It's classic Newton's third law. You step on the bathroom scale, you push down on the bathroom scale pushes up on you with an equal amount of force. And the reading on the scale tells you the amount of force it's pushing up on you with. 99+% of the time, you're going to assume that the scale is telling you your weight. And again, 99% of the time it is. If you're just hanging out in your bathroom and weighing yourself, the force you're pushing down on it is going to be your weight. And it's going to tell you the weight, which is fine. That's what it does. But the scale is actually answering a different question. The fact that it happens to be your weight most of the time is great. What the scale is really telling you is, hey, here's how much force you're pushing down on me with. Now, normally we use that to tell us the weight, but it doesn't have to be our weight. I mean, you know that you can just put your hand on a bathroom scale and push down on it really hard, and it might show like 50 pounds if you're in America. And obviously your hand doesn't weigh 50 pounds. So it can tell you a force that is not equal to the weight of the object that's pushing on it. So it's not that the scale really lies to you. It might just be answering a different question than you think it is. And it's important to realize that the number on the scale is not always tied to the weight of the object that's standing on it. Now that that's out of the way, let's take a look at when the elevator starts moving upwards from the bottom of the building. And already on the table, we can see that there's a force on Frank by gravity equal to -900 newtons. Again, that's never going to change. His weight is constant. The symbols at the bottom indicate that he has a velocity that's moving upwards now, and he has an acceleration that's directed upward. When your velocity and the acceleration act in the same direction, you do speed up. And how does that work? Well, the elevator motor increases the upward force on the elevator, all the contents inside, and the elevator wants to keep its contents accelerating upward with the elevator. And in order to do that, it exerts more force up on them in order to create an unbalanced force. So the floor of the elevator exerts a force on the bathroom scale exerts a force on Frank, and now Frank has a larger force acting up on him than he does acting down on him. That's required if he's going to accelerate upward. And Newton's third law tells us that if the scale is showing a reading upward of 992 newtons on Frank, then Frank must be also pushing down on the scale with 992 newtons. In order for the scale to accelerate Frank upwards, it must be exerting more force up on him than gravity is acting down. And the reading on the scale indicates that. Frank's weight has not changed. It is the same as it always was. But the reading on the scale, remembering that the reading on the scale doesn't always tell you your weight, it simply tells you how much force you're pushing down on it with, shows that there is a larger force acting upward on Frank. If we focus just on the forces acting on Frank, we can see that there's an upward force of 992 newtons. There's a downward force of 900 newtons. So the net force, which is the sum of the forces, is 92 newtons directed upwards, positive 92 newtons. If we use the equation F net equals ma, aka Newton's second law, we can solve it for the acceleration, plug in the terms, and we get conveniently 92 newtons, which are kilogram meters per second squared, divided by 92 kilograms. Kilograms cancel with kilograms and leaves us with a positive 1.0 meters per second squared. So the amount of force divided by the mass of Frank tells us the resulting acceleration in classic Newton's second law fashion. And as I mentioned briefly earlier, this corresponds to the idea that if your acceleration is directed upward and your velocity is directed upward, that's going to be associated with a motion that is speeding up. And if you're at the bottom of a building and the elevator is starting into motion, you are speeding up. You're gaining a positive velocity directed upward. So what does Frank feel as he's accelerating upward? He's in the bottom of an elevator, starting at rest, and now the elevator is starting to move up. Remember, Frank's weight has not changed, but the force acting up on him has increased. So Frank has this sensation that the scale is pushing up on him with more force than he's used to. And we don't really spend a lot of time in accelerating environments in our everyday life. We're kind of a non-accelerating kind of species. Often we're at rest or maybe moving with a constant velocity. The times in our day where we are accelerating are usually kind of brief, kind of fleeting, don't last very long. So we don't have a ton of experience in interpreting accelerations. We just usually put them in the context of stuff we're used to. So if Frank was just standing in a bathroom somewhere and he felt the scale push up on him with more force, it was probably for one reason or another that he was pushing down on the scale with more force. I mean, maybe he gained weight. Maybe he just had his finger sort of under the lip of the counter next to him, and he was sort of pushing up on the counter from below. Therefore, the counter was pushing down on him and adding a little extra force to the scale. Regardless, when the scale reads more, when we feel like the scale is pushing up on us, in non-accelerating life, it means for one reason or another, there's extra force pushing down on us. That's exactly what it means. However, when we are in an elevator, we are not experiencing sensations in a kind of a typical way. So when Frank feels heavier, that's the result of the floor pushing up on him more, but it's not the result of something extra pushing down on him. But that sensation he's still used to, so your body interprets it as like you feel heavier. Going a little bit further, like you can feel like your stomach drops a little bit. Actually, that's a little bit due to the inertia. You're in your intestinal cavity. You've got all these organs sort of suspended on these sinews and stuff like that. And as your body accelerates upwards, inertia sort of leaves your innards behind a little bit. So you do sort of feel sort of in the pit of your stomach like it's kind of sinking a little bit. That's because your body is accelerating upward for a moment without your innards, and then your innards catch up. So the sensation of feeling heavier, it's important to recognize that when you break it down, when you study it as a force combination, it is the result of an extra force pushing up on you, not down on you. Frank feels like there's more force pushing down on him, but in order to accelerate, he really needs more force pushing up on him. So his body interprets the acceleration incorrectly. Again, not illogically, but incorrectly. Okay, let's pause for a second. That's some heavy thoughts there. Good opportunity to pause, take a sip of tea. If you are in such circumstances where you can do so, you might be stuck in your physics classroom right now watching this with no access to tea. And if so, I apologize for that. But if you're not, why not brew yourself a cuppa? So now we're in the middle argument of the elevator discussion. You were at rest at the bottom of the building, then you accelerated upward to gain a positive velocity. And unless we're in the end scene of the original Charlie and the Chocolate Factory, and Willy Wonka has accelerated the elevator at such a crazy speed that it blasts through the building and flies off into the sky, most elevators, for good reason, don't do that. Most elevators just sort of get you to a certain speed, and they're like, okay, that's cool. We're now moving upward. Just hang tight, and we'll get you where you need to be in just a little bit. So Frank is moving upward in a normal, non-child endangering Chocolate Factory mode, And when you're moving upward with a constant velocity, your forces are balanced. So Frank, aside from the fact, I mean, I'm sure there's a little bit of jostling for the fact that he's in an elevator moving upward, but the forces on him have returned to normal. There's no need to have an extra force acting up on him because he's not accelerating up anymore. So the scale is just pushing up on him with a force that's equal to his weight. And the reading on the scale shows the reading that the scale is pushing back up on Frank with. And so Frank pushes down on the scale with 900 newtons. The scale pushes back up on Frank with 900 newtons, and it's all just kind of normal. As noted, 904 newtons. So what does Frank feel at this point in the elevator ride? Well, once it has reached a constant velocity, and again, that usually happens in a couple seconds after the elevator starts, you don't feel that sort of sinking feeling in your stomach anymore. You don't feel heavier. You just feel normal. And normal for us tends to be the fact that we are not in an accelerating environment. So yeah, is it normal for Frank to be moving upward with a constant velocity? I mean, probably not. Most times he's weighing himself, so he's probably not doing that. But you still feel the same as if you were at rest, because again, Newton's first law says, hey, as long as you're moving with a constant velocity, forces are balanced just like you're at rest. If you were driving a car horizontally and you knew that there was a red light coming up where you needed to stop, you wouldn't wait until you were right under the street light and just slam on your brakes. Elevators have to follow the same physics. So if an elevator wants to slow down and let you off on the 28th floor or wherever you're getting off on, it has to start slowing you down ahead of that point. Now, we are not going to use the word deceleration in transparent physics, as the title of the slide shows you. We are going to be talking about negative acceleration. It's negative acceleration that's required here because our velocity is positive. And if we want to slow down with a positive velocity, we need an acceleration that's directed in the opposite way. Remembering that we have two forces to make that happen. Frank's weight is always acting down with negative 900 newtons. And the elevator needs to slow down the elevator car and the contents in the car. So basically, it needs to allow the downward force to win. Almost kind of a controlled fall, if you want to think about it that way. And when the elevator exerts less force up on the scale exerts less force up on Frank. Now, the scale is exerting 845 newtons up on Frank. Frank is exerting 845 newtons down on the scale. And we can take a look at the forces acting on Frank specifically to see what that means for his motion. So focusing just on the forces that act on Frank, gravity is acting down with 900 newtons. The scale is pushing up with 845 newtons. The net force is the sum of these two forces, 845 plus a negative 900, means that the net force is negative 55 newtons. The net force down is winning, which is what we need because Frank's got to slow down. He's got to get off on his floor. We can put the net force into Newton's second law, manipulate it for A, solve it out, and in this case, the acceleration is negative 0.6 meters per second squared. So Frank's positive velocity is slowly going to decrease as he approaches at a point of rest. And when we have the combination of a positive velocity and a negative acceleration, you're going to get an object slowing down. As the elevator slows down, we get another one of those acceleration scenarios. And in this case, if you're moving upward and the elevator is slowing down, you might feel a little bit lighter. You might feel like your stomach's going up into your throat a little bit, depending on how rapidly that acceleration is occurring. And as always, it's important to remember that your weight has not actually changed. You're not lighter at the top of the building. I mean, unless the building goes up like 5 miles above the Earth's surface or something like that. But if you're in a normal building, your weight will not change appreciably going upward. If you were in your bathroom in a normal, non-accelerating house and you feel a little bit lighter, that's probably because there's some sort of force pulling up on you to sort of cancel out a little bit of your weight. If you're standing next to the counter, and maybe sort of a classic bathroom cheat is if you're weighing yourself and you maybe weigh a little bit more than you think you should, if you just kind of gently rest your hand on the counter and sort of push down on the counter, then the counter pushes that back up on you, and that's a little bit of your weight canceled out, and maybe your weight goes from 200 pounds to 190 pounds. You're like, there we go, I lost some weight. So you can definitely mess around with the numbers on the scale by exerting more or less force on yourself. So if you feel a little bit lighter, it's in a normal day, it's probably because something's lifting up on you. Maybe something's pulling up on your belt or something like that. In an elevator, we don't need any additional forces acting on you to explain it. The fact is that the motor is exerting less force up on you than your weight. It's a somewhat controlled fall almost as you're still moving upward. And just as when we accelerated at the bottom of the building, it's important to recognize the idea that you feeling lighter, you feeling like your stomach is sort of floating up a little bit into your chest, is not the result of a force acting, an extra force acting up on you. In fact, the force acting up on you has gone down, so that the force acting down on you is the winner. So it's another instance where you feel as if you're being sort of lifted upward a little bit, but it's actually an increase in force, relatively speaking, acting down compared to the force that's acting up. And again, we can talk about the idea of inertia and sort of the contents of your sort of abdominal cavity are moving upwards with a certain velocity. So as your body starts to slow down, there's a little bit of lag there, and they'll sort of move up a little bit, and you'll feel a little queasy. But it's not the result of more force pushing up on you. Okay, we made it. Frank is now on the 28th floor. The elevator has come to rest. The elevator doors are opening. And what does Frank feel besides exhilaration, having completed another successful elevator ride upward? Well, since he's at rest again, the forces are balanced. And since the forces are balanced, he doesn't have any of those sort of acceleration sensations, even though we interpret the acceleration sensations wrong all of the time. He is now at rest. So being at rest on the 28th floor is physically no different than being at rest on the first floor, and also the same as moving upward with a constant velocity. Your forces are balanced and you feel normal, because being non-accelerating is sort of our go-to move. Okay, quick pause, stretch, breathe, and we're ready to take that entire process and repeat it again, but this time on the way back down, starting at the top, working our way down, talking about all the accelerations. Just kidding, we are not going to go through all that again. You can see the length of the video based on the amount of time we talked so far and the amount of time that's left. Definitely will not allow for that. But I've given you all the tools you're going to need in case, say, your teacher asks you to do that. Because we've talked about how you feel and what happens when there's a positive acceleration. We've talked about how you feel and what happens when there's a negative acceleration. And we've talked repeatedly about how you feel when there's no acceleration. And that could be whether you're moving with a constant velocity or whether you're at rest. So you put all that stuff back together, and the physics of an elevator going up is the same as the physics of an elevator going back down. You just make sure you identify what acceleration is occurring, and you can match those sensations up on the way back down just like you did on the way up. So here's a quick hint if you're being asked to do this on your own, and if you're starting on the 28th floor and working your way down. You're starting at rest. As the elevator starts to move down, you've got a Speeding up in the negative direction. Speeding up in the negative direction is going to require you to have a negative acceleration. Once you've reached a certain velocity going down, you're going to have a constant velocity, constant negative velocity. As you get to the bottom, and this might be the trickiest part, you've got a negative velocity that you want to slow down. So a negative velocity that you want to slow down requires an acceleration in the opposite direction, so you're going to need a positive acceleration. And then finally, you're back at rest again. So match those accelerations to some of the scenarios we talked about going up, and you should be in good shape. A few thoughts to wrap this lesson up on. First of all, again, I hope you've seen that as always, if you found the content of this lesson helpful, please consider liking the video. If you have any questions about what was discussed, and it's entirely possible this can be a complicated subject, leave a comment. To find out more of what's coming down the pipe from Transparent Physics, click subscribe. And I hope I've made the magic of elevators a little clearer for you on this episode of Transparent Physics.